welcome guys. So in this video, I will try to quickly review the linear regression, and most importantly, I want to prove the normal equation for linear regression problem. Okay, so let's quickly describe the setting. So the setting is that basically we have like y1, right? So okay, so let's change it. So suppose you observe that the x11, x12 up to x1 p, right? And you see this is your factor, right? You see some independent factor, and you give you y1, and you also see the x21, x22 up to x2p, then give you y2. And you finally observe that the xn1, xn2 up to xnp, I give you yn. So of xij, yj are just real numbers, right? You start from here, and then the key is that we describe a model, right? So the model, the linear regression model, is basically I hope that yi will equals to, let's say, beta 1, beta 0, and the beta 1 xi1 with the beta p xip, right? So the number of independent variable is p, and there are total n data. So total n data. Right. So this is our model, and then there's an arrow turn, let's say epsilon I. So our goal is to find beta 0, beta 1 up to beta p. Okay, so this is the standard linear regression, and the idea is that just change it into the matrix, right? So the idea is that let's define y to be y1 to yn, and the x, right? This x is a matrix, right? So this is a vector, and I can change this x to be, let's say, x, right? x11, 12. I just parameterize my data as a matrix. So I just compose all my data, xn1, xn2, up to xnp. Right. So this is very easy. That you just combine all you have, right, and build as a matrix. So we start from here. Then also our beta matrix, So beta is what we want to compute, right? So beta 0, beta 1 up to beta p. Okay. So what we also, there's epsilon. So epsilon vector is epsilon 1. Epsilon 2 up to epsilon n, right? We total have n data. Okay, so we start from here, and we can think that this equation is basically looks like y, right? Y equals to what? Equals to x beta, right? So x is n by p, right? And this is p by 1, so it's x beta plus epsilon, right? So y is 1 by n. Right, so this is our equations. So our regression equations. Okay, so the idea. So let's see. So the idea is to make y minus x beta. Right. So I can compute a norm of it. Right. So I can compute a norm of each. So you choose one beta, right, and then you can compute a norm. So I want to make small to make this as small as possible. So find the beta such that this term as small as possible, right? So we just try to minimize this. And why this is doable, right? Because this is the square. This is the square, function of, for each beta, for beta 0, beta 1, right, up to beta n. This is the quadratic function of beta 0, beta 1, beta n. So the quadratic function can have the global minimum. Okay. So the idea is that this is doable. Okay, and how to prove this? This is called the least square square method. Okay, and also the normal equations. Okay, so let's quickly give the proof. Okay, so the proof is basically the normal equations. So this is usually written in the textbook or other like the other Coursera's method or something, right? And this is very famous results. So I will quickly give the proof of the results. Okay, so the fact results of what we want to prove is this beta will be xtx inverse xty. Okay, so this is the result. Okay, so this is the answer. Oh, sometimes I will omit this error just for convenience. Okay. So what we want to show is that this beta, right, will make what? Will make this y minus x, y minus this x beta as small as possible. Okay. So there are two proofs. Oh, let's prove the first one. The first one is using calculus. So using calculus. Okay. So our goal, let's say s of beta, will be y minus x beta squared, right? So basically it's the same as 1 minus y minus t, right? Minus x beta transpose, right? So since it is a number, right? Actually, so this right. So sorry about this. Yeah, because this is this need to be a number. So I write y as a column, y as a column vector, right? So to make it be a number, that it must be there must be yt times y, right? So then it will be 1. So 1 by 1 number, right? So this it will be yt beta t xt. Okay, and note that we are not assuming that x is symmetric, right? So x is not symmetric, usually not. Okay, so x beta will be yty minus x yt beta minus beta t xt y plus beta t x beta. Okay, and so this is a number, this is a number, this is a number, this is a number, right? So the number is transpose itself, right? So s of beta can be written as yty minus 2 beta t xty, right? Because these terms the same as these terms, because they are numbers. So if you transpose it, it becomes the same, right? So right now you just do the calculus of beta, right? To be more rigorous, you need to expand it as for each beta, right? So actually, you're going to do this for each beta I, right? If you do it carefully, then you see this term is vanished, right? There's no beta here, and this term is a linear, right? Become this. Also, and for this term, this is symmetric, right? This matrix is symmetric. So when you do the derivative, there will be two terms. Then you will get this, right? Because you vary with this beta t, and if you expand it there, this is symmetric matrix for this s of t. So there will be two terms, just like if you differentiate in respect to x squared, right? So this is the result. Then hopefully becomes 0. Okay. So you get xt beta equals to as xty. So beta is xtx inverse xty. Okay, so this is what we want to prove, these results. Okay, let's shrink it so you guys can copy it if you want to. Okay. So usually I will not preserve this board, right? Because I usually go to my own video and check what I already did. Okay, so the next is that the next way is that using the standard inner product space. So I like this method compared to calculus, right? Because in calculus you need to deal with these terms, and maybe you need to write down carefully to make sure that everything you did is correct, right? But if we using an inner product space, then there's no need to worry about this proof. Okay, so let's go back to S of beta, and then we check as this. Okay, so let's see how we can prove it, right? So I can define an inner product, right? Inner product space as a, let's say I define inner product space as somebody give you a, let's maybe using a color as, use this. So A and B to be ATXTXB. Okay, so this is my definition. So if preserve this is positive definite, then this is definitely the legal inner product. Okay, so S of beta can be written as YTY minus as this one, and this one. Right, so this term is just beta. Okay. Right, this term is just beta. Okay. And this is YTY, right? So that's this term is also important, but we just forget a little bit. So this term I want to write as this one, right? So then how should I write it? I should write it as Y, right? Yeah, an inner product with B, right? With this beta, right? But there's X here. So ideally, what I can get is X inverse X. Right? If you check it, this is just X inverse. Sorry about this. So this is X inverse X beta. Right? So these two terms cancel. Okay. And also for these terms, I can write it as the same way as beta XTX inverse XTY, right? Plus beta. That's okay. So this is we have 4 terms, right? Right, 4 terms. Okay. Right. So now we just try to make this beta, right? So we can change it into beta. Again, I want to combine these two. Okay. So by the way, the inner product space is basically can be changed across. So I can make this beta as beta minus XTX inverse. Let's shrink a little bit. Okay, so make sure everything is correct. So XTY beta minus XTX inverse XTY plus something. Okay, so why this is correct, right? If you expand it, you get beta, and you get minus beta with these terms. And then you get these terms with beta, right? You can exchange these two. So you see the first one is beta. This one is beta XTX inverse XTY. And then this term is XTX inverse XTY beta. All right. And by definition, by the previous argument, these two terms are exactly the same, right? So that means these terms. I can use these terms to substitute with these terms. So these two terms actually are the same, right? So that means I can just use this as this. So I can just replace this as one of these. Right. So that means this term is the same as these terms. Right. So these two terms are actually the same, right? Plus something. Plus this term of y, right? This is complicated, but these terms are independent of y. And also this term is independent of y. Sorry, independent of beta, because I already get beta, and these two term beta, right? So there's no remaining beta. Since I already get this beta, and I get this beta y, and I get this beta y, right? So there's nothing remain. So these terms are independent of beta. Okay. Right, they are independent of beta. So finally, right? So this is square, right? So this term are independent of beta. So to make this term smaller, right? Yes, in the product space, this term must be 0, right? The vector should be 0. So beta equals to x inverse xty. Okay. So that's the proof. Right, the proof idea is that this term is independent of beta, right? So once you remove everything, related to beta, then you can make this vector to be small, to be 0, right? So this is our normality equations. Okay, so that's it. So we have two ways to prove the normal equations. The first one is the calculus. The second one is just combines as an inner product space. Okay, that's it. And I will. So this is basically the simplest linear regressions problems. Okay, I will see you guys in the next video. Be sure to subscribe to my channel. Thanks.